Okay, hi everyone. My name is Chen Hao, and today I'll be going through this question. So the question is that you have a pump on the ground and it's pumping some water, and you want to find the minimum velocity and angle required such that it clears this wall, right? So this wall, it'll block water if it hits the wall. So you want to shoot the water over the wall. So this question is a good application of the parabolic motion such that you express y in terms of x. So I'll talk about what that means now. Okay, so in general for parabolic motion, right, you have a parametric curve of y in terms of t and x in terms of t, right? And it's given by kinematics equations. So one useful thing we can often do in such questions is we can often invert the x of t function to become t of x instead, right? And when it becomes t of x, then you can substitute this t of x, right, it back into y of t, then you can get y of x, right? So now instead of having a parametric curve, right, the first two equations over here are what is known as parametric curve, right? These are known as parametric curves. Instead of having a parametric curve, now you have a Cartesian function, right? You just have a graph y in terms of x, right? Like a normal graph. Okay, so now that you have this graph, this graph describes the trajectory of the water, right? This y in terms of x, the parabola, right? You can see it's quadratic in x, right? It's quadratic in x. So using this parabola, you can find out you can do some useful things with it. Okay, so in general, whenever you have parabolic questions, questions involving parabolas, this is a useful trick you can do, right? We don't like parametric curves because there's time inside. What if you want to see the shape of the graph, right? If you want to see the entire shape of the graph, like the entire parabola that the projectile traces out, then you express it in terms of in the form of y as a function of x. Okay, so what do we want to do in this question? So far all the results we have done is just purely standard projectile motion stuff. We haven't really even contextualized in terms of this question, right? But let's look at the question a little bit. So in the question, we are required to find the minimum velocity and angle required to clear the wall. So let's first imagine all the possible velocities and angles, right? So imagine I'm over here and the wall is here, and we just want to imagine all possible velocities and angles. So we're doing a 2D kind of search, right? We're trying all possible velocities, or then like some go very high, and trying all possible angles, right? Some of them could be very low like that, right? And in general, we want to narrow down our search space into a one-dimensional search space of sorts, right? So right now, basically, we are trying all the possible velocities, right? And we're trying all the possible angles. That's a 2D search problem, right? We're searching for something in 2D, right? But that's not very nice, right? So we want to narrow it down to 1D, and specifically, we want to narrow it down such that all the v naught and theta, every single value of v naught and theta would define a parabola, right? If I give you a v naught, I give you a theta, you can tell me what parabola exists, right? Given by the orange equation on the right over here, right? Given a v naught and given a theta, you can tell me the parabola y in terms of x. So now we want to look for parabolas. I claim that we want to look for parabolas that actually pass through the tip of the wall, right? And why is that so? The intuition is that suppose I have a parabola that um, flies over the wall, right? If a parabola that flies over wall, what's the question want us to do? It wants us to find the minimum value of v naught, right? The minimum initial velocity. So if I have a parabola that flies over the wall, I can actually reduce the velocity a little bit and have it still fly over the wall like this, right? And I can reduce it until, right, there exists for every angle theta, there exists some velocity such that it just nice touches the tip of the wall, right? And after that, I cannot reduce the velocity any further, right? And of course, I wanted to touch it because if it's too low, right, then it hits the wall, then it cannot pass the wall. So now instead of looking for all v naught and theta, right, instead of looking for this 2D searching instead of searching 2D parameter space, now I'm just searching, I want to reduce it to search 1D parameter space, right? So now for every value of theta, right, so now I've eliminated a lot of pairs of v naught and theta such that for every theta, right, so I give you theta, right, and you give me a v naught, right? You calculate some v naught that says at this angle you need to be at this velocity to clear the wall. Okay, and so how do we do that in terms of equations, right? In terms of equations, remember that the v naught over here must be such that it hits the tip, right? It hits the tip. The water hits the tip. Water hits the tip of the wall, right? And that in that case, it will correspond to having the function y of x pass through a particular point, right? And specifically, if we set this to be the origin O, right, 0, 0, then the coordinates of the tip of the wall will be 3, 4, right? 3 in the x horizontal direction and 4 in the vertical direction. So y of x passes through 3, 4. So I substitute that into the equation, and remember that for a quadratic curve, right? For a quadratic curve, 2 points would define, 3 points would define a curve, right? 3 points would define a curve. So currently when we substitute 3, 4 into the quadratic equation, we still have 1 degree of freedom left, right? And that degree of freedom is given by essentially theta, right? So to define a parabolic curve, you need 3 points, right? 1 point is the origin, 1 point is the tip of the wall, and the third point, right, the third degree of freedom is any point, but instead of choosing any point, right, that I want the parabola to pass through, I want to allocate that degree of freedom to the theta, right? So in this case, if we substitute in 3, 4 into the equation, we get this as a constraint, right, on theta versus v naught squared. And rearranging it, right, we can see that I'm going to rearrange it such that we have v naught in terms of theta, right? So if I want to say this, I can actually say that this is actually v naught in terms of theta, okay, where theta is this thing over here, right? So if I give you a theta, what the equation here is saying is that if I give you a theta, you will produce for me a v naught squared, right? The velocity naught squared, the initial velocity squared, that is such that if I project it with v naught and at angle theta, it will pass through the tip of the wall. Okay, so here theta is independent, right? Theta is an independent variable, and v naught is given by this formula, right? V naught is dependent, so we have v naught as a function of theta. Okay, so that's what this equation is saying. So you can do the math, but often it's useful to think what the math is actually telling you. Okay, and so if I look at this, and I'm gonna move the secant squared in the numerator to the denominator as a cosine squared for reasons you'll see soon. But I want to do this because now all the theta dependence is in the denominator, right? Because remember what was our goal in the question, right? So in the end, I get this expression. What was our goal in the question? Our goal was to minimize v naught, right? So if I want to minimize v naught as a function of theta, right? Minimizing v naught as a function of theta, I can take the derivative, right? This just becomes a 1D calculus problem. So but I can make some observations first, because if I try to minimize this, right, it'll be quite monstrous, right? Taking derivative of such a huge function. So we can make in physics, we can make the observation that minimizing v naught squared corresponds to maximizing the denominator, right? The denominator. So I want to find the angle that makes the denominator maximize. And to do so, I take the first derivative, right? So in physics, when we want to minimize or maximize something, often it suffices to do it in the first derivative. You don't need to show that the second derivative is positive or whatnot, right? So that's just for physics, though. For your math, your teacher will want you to show that the second derivative test holds. Okay, so anyway, now I just want to maximize this function, and to maximize this function, we can just take the derivative and we get the following, right? So what's nice about this method is that we have this thing set to equals to 0, right? And that gives us an exact value, right, for tangent to theta, right? So if I plug in the calculator, I get this value, right? Yeah, if I plug in the calculator, I get this value, but actually the question rounds off the values, but there was actually you can do it in exact form actually. Yeah. So anyway, I get this, and so this is the angle theta. Now we know the angle theta, right? And then we just need to substitute in theta equals to 71.565 degrees all the way back into the original v naught squared in terms of theta, right? Because remember we had this formula, and then we get v naught squared and we're done. Okay, so that's how you approach this that's how I would approach this question, by thinking in terms of number one, what is the parametric curve, right? Parametric curve x, y of t and x of t, right? And then number two, I don't like that, so I convert that into y of x, right? And that gives me a shape, right? And now using y of x, I can fit, right? Using y of x, I can fit a point 3, 4 onto it, okay? And so now 2 degrees of freedom are gone, right? Parabola is 3 degrees of freedom. Now 2 degrees of freedom are gone. One is 0, 0, the origin, right? Because that's the origin of the water jet. Another one is 3, 4, right? And so the extra degree of freedom, the remaining degree of freedom, is going to be the angle theta, right? And so for every angle theta, right? For every angle theta, I have a function velocity squared in terms of theta. And so that means that, once again, as I'll repeat that statement again, if the degree of freedom theta says that, okay, sure, you can choose any angle you want, right? But for every angle you choose, right, the moment you choose the angle, right, the velocity must be fixed, because the velocity must be chosen such that the water jet passes through these 2 points, right? So that's what's going on in the math. Okay, and so now that we have this, right, we can remember the degree of freedom is theta, and we want to minimize this, so we just do calculus, right, 1D calculus. So we have reduced essentially a 2-dimensional search problem into this 1-dimensional maximization problem, right? So we have reduced a 2-dimensional minimization problem into a 1D one. Okay, and then we do some tricks along the way. Instead of minimizing velocity, we actually maximize the denominator. Things like that will make your life easier. So yeah, that's it for this question. I'll see you in the next one.